Okay, this video is to go over the homework section, Chapter 2, Section 1, the self-check and the applying math, questions 1 through 7. I'm going to be going through the answers and the reasoning behind each one of them. Starting with number 1, infer whether the size of an object's displacement could be greater than the distance the object travels. To answer this question, we're going to consider two situations. First situation, you travel from A to B, and it is a straight line. You do not deviate. Second situation, you're still traveling from A to B, but you take a detour, and so your path is more broken, like this. If I were to draw arrows representing the displacement of each journey, case 1, the arrow exactly follows the path that was traveled. When the path and the displacement are equal, the displacement is equal to the distance. In case number 2, if I draw my vector showing displacement from A to B, notice it does not follow the path that was traveled. The displacement in case 2 is less than the distance traveled when you took that deviation. You can never get your displacement to be greater than your distance. It will either be equal to the distance if the path was a straight line, or it will be less than the distance you traveled because it is a straighter path. Alright, number 2, describing the motion represented by a horizontal line on a distance time graph. I'm going to draw a rather large one here because I'm going to reference it for a few other questions. So here's our distance versus time graph. Time 0 to time 1 to time 2, and let's throw in to time 3. I'm going to label these down here. At the beginning of the graph we have time 0, here's time 1, let me slide this up a little bit so you can see it. Here's time 2, and here is time 3. The horizontal line on the distance time graph stretches from time 1 to time 2. Well, what does that actually mean? Our distance does not change from time 1 to time 2. If our distance does not change, we can say that the object or person or whatever this was at rest or stopped. Alright, number 3. Explain whether, during a trip, a car's instantaneous speed can ever be greater than its average speed. Well, just to be clear on our definitions here, instantaneous speed, which I'll just abbreviate, is the speed at any instant in time. So if you were to look at a speedometer, this is what you would see. Speed at any moment or instant in time. An average speed takes all of your instantaneous speeds from an entire trip. Looking at this graph, you would take all of the speeds that this person was traveling at for the entire trip and averages them together. So it's the total distance divided by the total time. Now, why this is important is because an average speed just looks at the entire trip. So if you look at my graph up here that I drew in number 2, notice we have a period from time 0 to time 1 when we're moving at a constant rate. So every second I'm covering the exact same distance. Okay, so if I were to draw in those lines at every single second, I'm covering the same distance on the y-axis. That's how I know I'm moving at a constant rate. From time 1 to time 2, that distance covered is 0. I'm at rest. And then I resume increasing my distance from time 2 to time 3. If I were to look at this whole trip and say, if I drove starting at time 0 and ending up at time 3, if I made this trip without this stop in between, how fast would I need to travel? That's what we mean when we say average speed. So if I draw a line connecting my start to my finish, notice it is lower or shallower than our initial speed. It of course has a greater slope than our at-rest line because your average speed has to be larger. And it is slightly faster than our second interval, or excuse me, our third interval speed. This is because when we take an average, by definition, it has to fall between the lowest speed and the highest speeds. So the average speed must be less than the highest speed and greater than the lowest speed. What this means is your speed at any one moment in time can be higher than the average speed it would take for the trip. Let's say you took your speed at 4 different points in the trip. You got 20, 20, 20, and 40. Your average would fall between 20 and 40. The slowest you were ever traveling was 20. The fastest you ever traveled was 40. So if you made this speed at one single velocity, one single speed, that speed would have to fall somewhere in between those two numbers, those two values. And so to return to question 3, specifically what it's asking, yes, our instantaneous speed can be higher than the average speed. In fact, there has to be an instantaneous speed that is higher than the average speed, unless it's all equal. All right? Number 4, the difference between average speed and constant speed. Well, I kind of talked in depth about the average speed in question 3, so let's talk a little bit about constant speed. If something is constant speed, that is, it is covering the same distance over an interval of time. So if that interval is 1 second, every 1 second it covers the exact same distance. So you can see that on this graph here. Every second, if I measure how far it goes, that interval is the same. All of these intervals are equal. So this straight line positive slope represents a constant speed. Now to be constant, it has to be unchanging. We just said up here for the average speed, an average is for the entire trip, the entire journey. It doesn't have to be the same speed at any given point because, in fact, in this example, there are 3 different speeds. Okay? This one appears to be our fastest speed. This one is our lowest because it is stopped. And this line is slightly shallower, so if I were to show these lines, it's slightly shallower, so slightly slower than this first initial speed. We are below, we are less steep than our highest. We are steeper than our shallowest because the average falls in between. So constant speed never changes. Average speed is just your speed for the entire journey. All right? Number 5 is a little bit tricky. I'm going to draw a diagram that will help us picture this. If we're looking at number 5, it says you are walking toward the back of a bus that is moving forward with a constant velocity. So I'm going to draw a vector for the bus's velocity going towards the right of the paper. You are walking towards the back of the bus, which means you are behind the bus going in the same direction as the bus. Now, presumably, you are not moving as fast as a bus, and so I'm going to draw your velocity vector much smaller than the velocity vector for the bus itself. Now, what the question is asking us to do is sort of picture what you would see if you were a person on the bus, so from the bus's perspective for the first part, and from the ground for the second perspective. Well, if you were a person sitting on the bus, this is a little bit odd, but if you think about it, look out the back of the bus, you see the person is walking towards you, but because you're moving faster than they are, they appear to be moving backwards. This is simply because the bus is moving forwards faster than this person is moving forwards. And so think of this vector as canceling out part of this one. you still have a lot left over, which means if you were to imagine this person as being stationary and the bus moving forward with this much velocity instead of this much velocity, it's still moving forwards. And you appear to be getting further and further and further away. Why? Because the distance between you is increasing. If you were a person on the ground, your perspective would see that both the bus and person appear to be advancing in the same direction. However, what you would notice is that the space between the bus and the person would increase. Why? It goes back to our velocities. You're moving with less velocity than the bus. And so from an outside observer's perspective, you're both moving in this direction to the right, but the bus is doing it faster than you are. It's covering more distance in the same amount of time, and so the space between you and the bus is constantly increasing as the bus pulls away from you. Alright, moving on to a couple of calculations. Number 6 says Machiko walked a distance of 1.6 kilometers in 30 minutes. Find her average speed in meters per second. So we've got a couple of important pieces of information. We have our distance is 1.6 kilometers. Our time is 30 minutes. And we're looking for speed, but we're looking for it in units of meters per second. Notice these units do not match the units that we're given. So before I can do this problem, I'm going to do a couple of metric conversions, and we'll change that 1.6 kilometers into meters. Kilometers means 1,000 meters, so I multiply by 1,000 meters per 1 kilometer. Kilometers cancel out. I multiply the 1.6 by the 1,000 to get my answer. 1600, 1600 meters is our distance converted into the right units. Time starts out from a given information of 30 minutes, and we're trying to get it into units of seconds. So to convert into seconds, I know that 1 minute has 60 seconds in it. And so I'm going to multiply 30 by 60 to get 1800 seconds. And now that's our time in the correct units. Speed, now we can go and actually calculate speed, is distance divided by time. If you prefer the triangle, remember our triangle looks like this. And we would be covering up speed, distance over time, d divided by t. So my d is 1600 meters. My t is 1800 seconds. I divide 1600 by 1800 and I get 0.88 repeating, so about 0.89. My units, meters, divided by seconds. There's nothing that cancels, so 0.89 meters per second would be my average speed for number 6. Alright, number 7 says a car travels at a constant speed of 30 meters per second for time of 0.8 hours. Find the total distance traveled, so we're solving for D, in kilometers. Alright, so we'll notice a couple of things. Number 1, our speed is in units of meters and seconds. Our time is given in units of hours, and our desired distance is in units of meters. I'm going to convert our time before we do the problem. That way I can just plug into the speed equation and solve for distance. So 0.8 hours, we need to get into units of seconds. Now if you happen to know how many seconds are in an hour, which is 3600, you could plug that in right here. Or you could simply do a two-step conversion and go 1 hour has 60 minutes and 1 minute has 60 seconds. Cancel out your hours, cancel out your minutes, you're left with seconds. 0.8 times 60 times 60, so 60 times 60 is 3600, times 0.8, and we come up with a time, in this case, equal to 2,880 seconds. So now we have the correct units of time for plugging into our speed equation. Now we're solving for distance in this case, so again, come back to our triangle, speed, distance over time. I'm solving for distance. Speed multiplied by time is our formula. And so I take my speed at 30.0 meters per second times the time, which is 2,880 seconds that we just calculated. Multiply this out, and you'll find that there are 86,400 meters traveled. Now this 86,400 meters is not our final answer because we want our distance in kilometers. So there's one more conversion we do. This was meters. There are 1,000 meters in every 1 kilometer. I write the 1,000 on the bottom to cancel out my meters. I'm left with units of kilometers. 86,400 divided by 1,000 is 86.4 kilometers. And that's the final answer for number 7.